Good afternoon, everybody. Welcome back to lecture number 14. So last time, what did we talk about? No, so before last time. We talked about the dynamics. This is what's, I would say, important. I'm trying to bring new information. So read this document. You have to study the whole Word document, okay? You have to read it. It's not only the slides, you have to read it, understand, and if you have any question, let me know. But it starts with the definition of stability. We all remember the difference between steady-state stability and transient stability. We started with the stability analysis with the maximum equation of the power. And do you remember this example? We had a generator, and where is XS, inside or outside the circle? Inside the circle. We have the transformer and we have the transmission line. And we noticed that if you reduce X, you increase the maximum power that you can transfer at 90 degrees. Will in real life operate at 90 degrees delta? No. But our, let's say, 80 or 75% that we would operate would have a higher power transfer capability. What else we talked about? We talked about the equivalent circuit. We want to operate it, say, at region A at equilibrium, which is point A or C. C is equilibrium, but not stable. A is equilibrium and stable. B is not equilibrium, and this is borderline stability. Get it? And we claimed before that the mechanical power equal to electrical power at A and C. So if electrical power, which is the power that crosses the air gap minus the stator losses, copper losses, which appears on the shaft, is equal to the prime mover, the diesel engine, for example. When we have delta increase, our delta P with respect to delta is positive, so it would bring our operating back to stability region. Okay? The opposite is true. At point C, if delta increases, P mechanical will be electrical, and we will have acceleration which will increase the angle. At point C, we will move away from stability. While at angle A, if we increase delta, your equation would bring it back, okay? So methods to improve stability: increase excitation voltage, reduce reluctance of the network. What other thing we have? We have the swing equation. The swing equation is inertia times the rate of change, the second moment, or the acceleration of the angle. So take the derivative of the angle function 2 times would equal to the acceleration torque, which is mechanical minus electrical. Keep in mind that measuring the torque is much easier. So these are the quantities. We have J is moment of inertia. This is measured. What's the unit of inertia? Kilograms? Over meter square or something? It has a unit. Yeah, whatever. Go to physics 101. What's the unit of theta? Is in radians. It's the mechanical degrees. And what's the relationship between mechanical degrees and electrical degrees? Theta E would be equal to P over 2 theta M. Okay? Or theta M equal to P over 2 theta E. If you have 4 poles, your electrical angle is half of the mechanical angle. It's half of the diameter of the circle, because half of the poles would cover what's equivalent to 360 degrees mechanical. It's not important now. So when the torque, the acceleration torque is positive, net accelerating torque, speed will increase indefinitely. When the net decelerating torque, speed will decrease indefinitely. So define theta M to be omega Sm, which is synchronous speed of the machine in radian per second, times t, plus some delta M, which is the mechanical angular displacement of the rotor from synchronously rotating reference in radian. This is another quantity. So theta would change over time. At time 0, theta m is delta m. That's your reference. Which, as I mentioned to you before, is the displacement where the rotor pole is aligned with the stator. The south pole of the rotor is aligned with the north of the stator. The rotor south is aligned with the north. If you increase it, you increase delta m, your initial angle. So this initial angle is the angular displacement of rotor from synchronously rotating reference in radians. What is the synchronously rotating reference? اللي جاء من الستيتر اللي هو الماكسيمم of the stator flux. Okay, you don't need to know the details about it, but did you get it? What is rotating, rotor or the stator? Rotor. No, the magnetic field, which one is rotating by itself? The stator. So the rotating magnetic field would have an axis correspond to the peak. The peak would move across the parameter of the machine. The displacement between the rotor maximum point with the maximum point of the stator is delta m at time 0. If time changes, we change with omega, where omega is 2 pi 60. 2 pi 60 is the mechanical synchronous speed of the machine, which is 120 f over p converted to omega. Take the derivative. So the rate of change of theta m would equal to omega sm, because t is gone, the rate of change of delta tm. Take the second derivative with respect to time, you will notice these two terms will equal. Plug this term, substitute this term here, so you will have equation for motion becomes as a function of delta m, not as a function of theta m. Then define omega m to be, this is by definition, the rate of change of theta m with respect to rate of change of delta t. Then you substitute this second derivative. If you take this derivative, you will have an omega here, and then you will have this one here. Anybody can guess how did we get this term? How did we, oh, this is power.
Yes.
So multiply by omega, that's why we got this omega. Get it? Because we transfer from torque to power. So J omega m is the angular momentum of the rotor, defined by definition m to be J times omega is the inertia constant. Now what will happen is, if you substitute J omega m with m, you will have this equation. We assume machine rotor speed does not vary greatly from synchronous speed. Then defined by definition h, which is the inertia constant, is the energy, which is the kinetic energy, الطاقة الحركية. Do you remember الطاقة الحركية half كا ح تربيع? Is it half كا ح تربيع؟
حركة.
ما أدري طاقة كتلة ضرب الحركة. لا.
نصف الكتلة وربع
السرعة. Whatever. But this is similar, but as definition of the inertia. الطاقة الحركية, potential energy. Kinetic energy, not potential energy. Then what do you have? Divided by the rating, the apparent power. So you're dividing it. Kinetic energy over MVA. Okay? Now, this is a megajoule over MVA. Megajoule over MVA. Joule is energy, MVA is power. Energy over power is what? Time. Get it? Isn't it?
Yes.
So that's why half joule. So then you go next to H is the inertia constant. The unit of H is in seconds because it's time. H is preferred over M because its value is within 1 to 10. Do you want this question in the exam? Why H is preferred over M? Or you don't like these questions? You want just problems? There should be some theoretical problem. If we make it problems, then it will be boring.
دكتور وش الفائدة إنه يكون 1 ل 10؟
Hmm?
وش الفائدة إنه يكون 1 ل 10؟ الرينج.
It's easier to scale. So for example, if you want to design a machine, you have 1, 2, 3, if we have 10 values, then if you have a range of 1,000. So this is for design purposes. And it makes more sense. But not only that, because I told you that the other reason is measuring power is easier than measuring torque.
دكتور 1 to 10 seconds.
Yes. So think about it's the time that it takes the generator to operate. The whole mechanical momentum at least becomes stable. Substitute, you will have 2h over omega m. Substitute from where? From this m. So what is m? M is what? hs over 2. But here you already divided by s. So you will have 2h over omega m divided by s divided by s. Because h has by definition division by s. This is algebra. The electrical angles relate the mechanical angle. This is the electrical degree. Is p over 2 times the mechanical degree. This is the equation I told you about. Where p is the number of poles. American way, not pole pairs, the British way. Simulink uses pole pairs, which is basically big P, giant P. Do you know the difference between pole pairs and poles? Poles is 4. What's pole pair? 2. Which one should we use in Simulink? Pole pairs. Which one should we use in this course? Poles. So in terms of electrical degrees, this would become 2h over omega s times the... Note that if we divide power over s, it becomes per unit. Because we're dividing it by the rating. This is like S base per unit. So this equation is called the swing equation, where delta is in electrical degrees. So this delta, what is it? This delta is electrical. This omega electrical, not mechanical. The omega we had before is mechanical. This omega is what? Electrical. Which is, okay, let me make a correction. This one is 120 F over S. You convert it to omega by multiplying it by 2 pi over 6. So if you recall this equation, write it down so you don't forget. So omega is electrical in radians per second. So you should put NS first. This is omega S. Omega here is, this omega is omega S. That's the shit. It's 120 over S over P. And then omega S is 2 pi over 60 in S. The one we had earlier with the torque was the mechanical. So to get the mechanical, it is, you have to measure how much mechanical rotations. Clear? So this omega SM is mechanical. Go back to the definition. Omega M is the mechanical synchronous speed, not electrical. So we convert everything to electrical. 2 times H times omega over omega S times the rate of change of omega S. This rate of change is the rate of change of the electrical frequency converted to radians per second. And then you just subtract the powers in per unit. So this is the swing equation where everything is electrical. So the swing equation is usually expressed in 2 first order forms. So instead of, so you calculate delta T over d delta over dt is omega minus omega S. Now you can write omega S is 2 pi f, where f is 50 or 60 hertz. Then you can substitute instead of d omega, you have d delta, where delta is, you remember EF equal EF angle delta. It's this delta. It's the phasor. So this is electrical quantity. So we have everything as electrical. What is the delta before? It's the one, I think it's called delta. It's the one here. Theta M equal هذه delta sub M. M means mechanical. What's the difference between delta M and delta?
Electrical.
One is mechanical, one is electrical. The electrical, you calculated it by measuring the voltage, EF. You measure VT, you measure AI, you know EF from the electric circuit. So the swing equation now, we have transferred every mechanical thing from mechanical engineering to everything electrical. And these are the two equations where one as, I don't know why we have this as 100, this is pi.
1 radian, 1 degree.
Oh, this is one for radians. So which one for coding?
Radian.
Radians. Which one for simple calculator?
Degrees.
So you use whatever you want. If you want to get your, this is a differential equation, right? How do we solve differential equations?
Laplace.
No, you solve differential equations using, don't do Laplace, using Simulink. Okay? Any question? So this is how to study this document. And then there is some comments. We went over the comments last time. Here is an exercise. You want to do this game? So for a synchronous generator, if the mechanical power input increases instantaneously, the machine will, let's guess what will happen. We have a synchronous generator. If we increase the prime mover power, okay, لحظيا, what will happen?
Speed up.
It will accelerate. It makes sense, صح?
Yes.
Does it make sense to decelerate or back? No, this is an easy question. For a synchronous generator, if the electricity power increases, what will happen to frequency? Stay the same or increase?
Still the same.
Decrease. Unless you have frequency control. It's decrease.
Why is that?
Why do you think?
Maybe because of the slip or something.
Hmm?
Slip.
It has to do with, if you increase the power, you reduce the power factor. If you reduce the power factor, you increase the power factor. If you increase real power, you increase the power factor. What will happen to IA?
Decrease. No, increase.
What do you think? For synchronous generator, if the electrical power increases, what will happen to the frequency? Okay, what was this question? Mechanical power. What is this question? So it means if you increase the load, your speed will change. What else we have? The swing equation can be expressed as, memorize it. This is for the degrees. Here, remember, here we have F. He dropped the F. Trick. Here it's 18. The machine operates at steady state synchronous speed when the powers are equal. So these questions, you will see them in the test, okay? Okay, study them, okay? What else we have? A summary. No need to read about the summary. So this is what I meant about decoupling. This is electrical. So this is EF, which has the delta. And if you measure the mechanical movement with the inertia, you will have the omegas and deltas. So this document is very important, okay? Any question about the document? You have to study it, okay? So we have how many slides? 74 slides. When is the major exam? After 15 days. So we have next week. So I would say the exam is up until the material of 24. No? Okay, 22 بس maximum.
It is the foundation day. Okay.
خلاص مشت خلاص 19 خلاص. No, we will have a help session maybe online. Maybe here. This help session material will be included in the exam, okay? It's not help session, it's we will solve. بصير في تلميحات, okay? So you have to, we will make it online, not in person. Maybe one of these days. So the exam here, right? Wednesday. So this lecture, do you want us to cancel it? No, not cancel. We will never cancel. Do you want us to make it online
Yes.
or this 19th?
Both.
So anybody traveling by airplane? Where?
Tabuk.
Did you book? Did you buy the ticket?
No.
Anybody else is traveling? We will make this in person, and you watch the YouTube later. And this one we will make it virtual. عشان متأخرين في المنهج. Okay? ما أدري في عيد أو شيء. I don't know. So هذه جلسة يوم التأسيس. Is this vacation 19?
22.
So only 22?
Sunday.
So we will think. So this is virtual. We will think about this. I don't know. Okay? Let's continue the swing equation. So what matters in the swing equation is what's in the slides. And this is what is in the slides, is we have the equation here for radians. You have the equation for degrees in the Word document, and we have delta T. So let's see an example. Example number 7. It's very important to watch this example. A 60 Hz synchronous generator. Calculators having inertia constant of 5 seconds and a transient reactance of xd, where d here stands for the direct axis. We'll talk about it later. It's connected to an infinite bus as shown in the figure. So we have xt transformer, we have xd, I'm sorry, this xd is for the generator, transformer, 2 transmission lines. Okay? So this is, where is the xs, which is xd, is inside the circuit by understanding. Reactance is marked in the figure per unit, the generator delivering real power 0.8, reactive power 0.07. So this is rated or operating. The 0.8 plus j 0.074. This is operated. So S would equal 0.8 plus j 0.074 MVA. No, per unit. Not MVA. Infinite bus voltage at 1 per unit. Find the power and power angle equation. What is the power? So let's see how he solved it. So this is the power at the load is 0.8 plus 0.074. So the transfer transfer reactance between the generated voltage and the infinite bus, the whole reactance, is what? 0.3 plus 0.2 plus 0.15, which is the parallel combination between 0.3. So that's why we have x to be 0.65. Now, the apparent power is this quantity, 0.8 plus j 0.07. What can I calculate? If I know the voltage, I need to calculate. I know the power, I calculate IA. So what is the equation? S equal 3 VI conjugate. صح ولا غلط؟
شيل 3.
غلط. 3 is nothing per unit. So what is I? Is S conjugate over V conjugate. If you note here in the example, S over V, what is V conjugate?
V.
V1. So 1 angle 0 conjugate is 1 angle minus 0, which is 1. What is S conjugate? You replace this with a minus sign. So that's why we have a negative sign. So what is E? E now EF is VT plus or minus, is this a generator?
Plus.
Yeah, right.
Plus JX, this is X total,
Times current.
IA. So it is 1 plus J X total, what is X total? 0.65 What is IA? 0.8 minus J 0.074, and you should get EF to be verified, trust but verified. 1 plus J times 165 times 0.2 minus J times 0.074, and I'm getting the same. No, I'm not getting.
White's 0.22, should be 0.8, I think.
You're right. 2 is 8. This is 8. So is this positive delta or negative delta?
Positive.
Positive.
So it's 117 per unit, angle 26.4 per unit. So this is your EF. And the power angle is 26, which is 0.46 radians. So the question is asking about find the power and the power angle. So what's the power angle?
26.4.
Now you need to find the power. How to find the power? Two approaches. Either you use the equation, which is power equal EF VT over X.
Delta?
I think it's X total, yeah, because you're studying the whole system. Remember, whatever you connect to the transformer or to the generator, transformer transmission line should include it in your calculation. So that's the equation. You have EF, you have VT, you have X, you have sine delta, which is the 1.8 times sine delta, which is that's the power. You can substitute the power. What's the maximum power? Put sine 90. What's the power right now? It's 1.8 times sine 26.39, which is 0.8. What's the unit of 0.8?
What?
No, per unit. What's this unit? Per unit. So you can deliver 80% maximum, 1.8 per unit, and you can, for this delta, you have 0.8. Clear? What is the other way of finding the power? You have EF times IA. EF times IA, you find S at the EF part itself, but use this equation because it's faster. Now, what is the other equation? Calculate the initial, if three falls occurs at bus 1, write the swing equation during the fault. So part B, during the fault, if a short circuit occurs, what will happen? If a short circuit occurs at bus 1, لو حصل عندي short circuit, what will happen? All of my electric current that comes from the generator will go toward the ground at the fault location. Who studied power protection? None? None of you took the course of Dr. Abidu? So if a fault, here's the thing, rule of thumb. If a fault occurs at any point, you assume that all the current would go into the fault location. The contribution comes from the generator, and contribution comes from the infinite bus, all the way to the faulty bus. So bus 1 would become like a magnet. It will take all the current. So if it takes all the current from the infinite bus, would it harm the infinite bus?
No.
No. Would it harm the generator? Yes. That is why we have PE during the fault to be 0. Does it harm the diesel engine? No. No. Does it harm? Why? Because the diesel engine is separate from the electric circuit. It's mechanical output. You're still burning fuel. Would it matter if a short circuit occurs on the electrical side? So what will happen is we will have an imbalance between mechanical and electrical. So the swing equation becomes H over pi times F0, which is 60 Hertz, times this acceleration equal to mechanical power. What is the mechanical power we calculated here before? At part A, not maximum, at this angle, 0.8. So at equilibrium it will be 0.8 minus 0.8. So you will have, at equilibrium, you should be having, so this is at part A, or equilibrium, you should have h over pi f0 delta square, the second derivative of d delta per time would equal to 0.8 minus 0.8, which is 0, so the acceleration is 0. But right now there is electrical fault, so that the equation, what we have here, what will happen, the swing equation, it will be 0.8 minus 0. So it will accelerate or decelerate? Accelerate, لأنها positive. So at part B it will be acceleration. So this is the swing equation. So part B, what did he ask in part B? Write the swing equation during the fault. Maybe I come a question in the test, and that's why you have to watch YouTube in these such moments. What will happen if I tell you, if there is some imbalance where the electrical power becomes 0.4? What is the swing equation? The swing equation will equal to 0.4 because it will be 0.8 minus 0.4. What will happen if PE is becoming 0.2? What's the swing equation? 0.6. Get it? So these are the questions. Part C, now we wrote the equation. What time is it? Part C is calculate the initial acceleration. Is you have to calculate this delta, which is 0.8 times pi 60 over h, which is 13.16 radian per second squared. 13.16. Can anybody convert it to degrees? It's 180 over pi times 30.16, which is 1,728. So it will rotate. This is not an angle. This is a very fast change of angle. يعني شو أشرحها لكم؟ The acceleration in 60 hertz is like that, صح? Convert 60 hertz to radians.
6 hertz.
This is acceleration, تسارع. You can't imagine it. بس إنه it will be like that.
60 hertz to radians تبقى في
لا 60 second, 60 radians per second يعني, just to imagine. Anyway, you can't imagine. Can you imagine the acceleration? No. Can you sense it? It's a result of the change of the speed. So this one is the result of the change of the speed, and then you will observe it as the change of the angle, the second moment. So this acceleration is very high. Now we will see an example here. Part D is calculate the power angle at 12 cycles after the fault occurs. Here is one information about power system protection. If you cannot clear your fault in 12 cycles, you will cause fire. What is one cycle? 1 over 60, صح? Because in 1 second you have 60 cycles. This is one cycle. What is 12 cycle? 12 times. What is in time 12 cycle? 12 over 60. صح ولا لا? What is 12 over 60?
1 over 5.
Which is 0.2 seconds. Clear? So can we translate 12 cycles to second? One cycle is 16.6 milliseconds. 12 cycle is what? 0.2 seconds. So what will happen here in this part is I go back to the equation. Now he's doing things I don't like, which is integration. So for 60 hertz system, 60 cycles is 0.2 seconds. Integrating it twice to get the delta function. If you integrate it twice, you will have delta would equal to the acceleration times t squared over 2 plus delta 0. What is delta 0? 0.46 radians. Where is the 0.46 radian? This one. This is delta zero, your initial angle. So if you write it as a function, it will be the acceleration times t squared over 2 plus delta zero. If you plug it, you will have it at 60.92 degrees or 1.063 radians. So this is if the fault clears at 12 seconds. The question is asking about calculate the power angle at 12 cycles after the fault, assuming the fault keeps persisting. مش يعني clears after 12 مش clears في 6. لو حصل clearing في 6 حنرجع للsteady state. And this is assumes the fault stays all the way past the 12. What is the at 12 cycles after 0.2 second, what is the angle of your EF? You can calculate it using the swing equation. So swing equation is, we wasted the whole 5 weeks to understand why swing equation matters. It's the most important aspect in these 5 weeks. So this example will come in the exam. Okay? Okay? I will change some part of it. Maybe I'll bring it the same, just changing numbers. So mark this example as what I call them a VIP, very important example. Why? Because this is not similar to EE360. We're learning something new. Now we know how to mathematically predict what will happen to every generator if there is a fault. I can develop some analysis using the swing equation by knowing my initial delta, by knowing when the fault occurs, etc. This is very important. Okay? So any question about this example? So these are the practice problems. We will reserve them maybe in the help session. Not today. The last practice problems is you have to do it by المنقلة. You can't do it by because you have two unknowns. So the only way is to draw phasor diagrams. We will talk about it. If it's gonna come in the test, I will give you a warning, okay? But for now, for the sake of material, let's explore new material for now, okay? So I expect the help session to at least discuss these 5 practice problems. Plus the question that will come in the exam. What is the question that will come in the exam? حق swing equation. It's very important. In homework 2, we will have 2 problems. The second problems, you have to watch the previous lecture. The first problem will be about swing equation. 2 problems, that's it. And I will give you 2 weeks, well, 10 days, not only 1 week, okay? How many days? 10 days is more than enough? 1 week is not enough. 10 days is more than enough? Okay, maybe we'll give you 10 days to 2 weeks, depending on the time حق الإكزام. So let's explore another type of machines. All our previous analysis, what did you assume about the rotor? Circular shape. So the air gap was uniform across all the deltas, صح? Here at salient pole, the rotor shape is like a rod with 2 circles at the end. For the salient pole, the air gap here between the north and the direct axis, so let me zoom. Do you see it? Do you see this figure now? Is it clear?
Yes.
In the salient pole, the air gap here does not equal to the air gap there. So we will have a problem. What is the problem? Our deltas, we should have 2 components rather than 1 component. Because my x of s, if I'm at this position, would be different than x of s if I'm at that position. So x of s will change. You cannot have it, because what is x of s if you recall? X of s, this is not required, I'm just trying to explain the concept. So x of s is a function of the reluctance, right? صح ولا لا? You remember E360?
Yes.
The reluctance is what? L over mu A. So if L changes, X should change. L, would it include the air gap?
Yes.
Yes, because the L would include the length of the core plus the gap, etc. So if the reluctance changes because the air gap, the parameter G, if you remember, changes in the salient pole machine. We are not going to dig deep into the mathematical analysis, but we will walk over it, okay? This is hard. So we have two axes, direct axis and the quadrature axis. هذا العمودي على الفلux axis حق الروتر. Where is the flux axis of the rotor? Is the direct axis. Where is the quadrature? Is so look at the direct axis. The flux would go through salient pole rotor. This would be a south. This would be a south. And it will walk over the core. And it closes the path of flux. This is the direct flux. Quadrature flux is another component here that I can measure where it crosses the axis horizontally and goes and closes itself. So this is the flux path that is quadrature. Quadrature to what? To the salient pole magnetic axis. Get it? Clear? So this is where Q and D axes comes from. They are used in industry. They are used in Simulink. So Q is quadrature. So what will happen? What will happen is, instead of calculating x of s, I'm going to have two components where I have x of s equivalent like, because I don't have x of s, I would have an inductance due to the direct flux path, and I will have an inductance due to the quadrature. But there, in this, there is no closed form formula where I calculate it. It has to be calculated using only the phasor diagram. How? I decompose I of A to D and Q. Look at the phasor diagram here. I have here, we usually have VT at 0, صح? Here I'm doing not a mistake. To make the analysis easier, I'm making EF to be at a reference, V of T at delta. So is this motor or generator?
Yeah.
Generator, because the delta itself is positive, an EF form. This is my IA. Do you see it? Can I decompose it into two components, D and Q? Where if you do the vector calculation, IA is the vector ID plus the vector IQ. Can I do that?
Yes.
قبل الكاس الجاي دكتور.
Yeah. So we'll continue next time, okay? We'll continue this online. Okay, and then I will try to. Any question?